Well, I wanted to thank Alex and Frederic for giving me this stimulating opportunity. I'm Federico. I'm a PhD student with Professor Kerenidis and Eleni Diamanti. However, this work is a collaboration with Queen's University in Belfast with Dr. Mancino and Professor Paternostro. So this work is in the context of quantum thermodynamics, and some of you may ask, why should we care about quantum thermodynamics? Well, thermodynamics is an exemplary theory that was started for dealing with practical motivations for technological innovations such as thermal engines. However, it gave rise to some of the most fundamental concepts that are relevant in all branches of all domains of sciences. And it is the physical theory most deeply connected to information and computation. Put in the words of Charles Bennett, computers may be thought of as engines for transforming free energy into waste, heat, and mathematical work. No system is isolated, so any realistic physical models require the introduction of thermodynamics in some sense, even, for example, just considering the fact that in quantum physics, in practice, the operations are never unitary if you do an experiment. There are many technological applications ranging from quantum thermodynamics that might be closer in reach than a universal fault-tolerant quantum computer. This doesn't mean that, of course, quantum computing is not important. It is fundamental, but we are making many progresses, but we still have a long run to go. And there are many other applications of quantum mechanics that could be interesting. Notably, energy waste is a crucial issue in modern society, so energy waste is what thermodynamics is effectively studying. So let's revise a bit of the foundations, so the theory of thermodynamics in general, and put some quantum ingredients in it. So the zeroth law of thermodynamics is about equilibrium. If two systems are both in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. So this statement is saying that there is an equivalence relation between systems is given by thermal equilibrium, and so I can classify systems that are in thermal equilibrium and give them the same label or the same parameter that I can call temperature, that can effectively becomes an empirical parameter, and I can parameterize this in many different ways. Normally we call it temperature, but it can be beta, which is the inverse of the temperature, or it can be even it is associated, for example, with the purity of a quantum system. A closed system in thermal equilibrium is described by a probability distribution in classical physics and by a density matrix in quantum physics. Closed system, by closed system, I mean a system that can exchange energy with the surrounding, with the environment, but not particles, not mass. So you can imagine a small system that is in contact with a large environment, and they are at different temperature. The environment is so large that it will not be affected by this small system. However, this small system, after undergoing complex dynamics, will eventually reach a steady state in which dynamics will not change anymore, and the temperature of the two systems is the same, so the systems are in equilibrium. Then another important law of thermodynamics is the so-called first law, stated this way. So in a thermodynamic process involving a closed system, the increment in the internal energy is equal to the sum of the work done on the system and the heat accumulated by it. So put it simply, is this formula. So the internal energy difference of the system is given by the work the experimentalist is performing on the system, and some energy exchange that the experimentalist cannot control, and is given by the surrounding, by the environment. I just want to give you a simple derivation of this principle in quantum mechanics. So we are in a closed dynamics, but we still allow for energy exchange, and this is the global dynamics given by the sum of three Hamiltonians. So one Hamiltonian is governing the system that we can control, one Hamiltonian is governing the bath, and another one is controlling the interaction between the system and the bath. The global dynamics is given by the von Neumann equation. It's a unitary dynamics. However, if we want to look at the dynamics of the single system, we need to trace out the degrees of freedom of the bath. before doing this, we make another assumption, which is a Born Markov approximation, which is simply assuming that there is a weak coupling between the system and the bath, and so at all times they are uncorrelated. So they interact, but they are always unentangled. By applying these two to this equation, we get the Lindblad master equation, which is simply describes the dynamical evolution of our density matrix and divides it in two parts. One is the unitary part and one is a dissipator. So if the interaction between the system and the bath goes to 0, the dissipators goes to 0, and the dynamics is completely unitary. Now let's make some energetic considerations about this. So the average energy of the system is simply the average value, or the mean value of the Hamiltonian on the system. And we can derive this expression, and by using the Lindblad master equation, just we put it here, we get two terms, two contributions. One is a heat current, and the other one is a power. So if we integrate this, we get the energy difference between the final state and the initial state. And we see, again, these two terms. One is the mean value of the derivative of the Hamiltonian. So in order to change the energy of the system, we need some Hamiltonian that changes in time, otherwise energy is conserved. And this is something that we can control in laboratory. So this is the term that the experimentalist is controlling, and that will change the energy of the system in an engineered way. And the other one is something that we cannot control, so is the heat current. So we reproduce this law starting from simple quantum mechanical considerations. So at the beginning, I said that there is a deep connection between computation, information, and thermodynamics, but we didn't see so much so far, because this is most deeply connected with the second law of thermodynamics, which says that the total entropy of an isolated system can never decrease over time and is constant if and only if all processes are reversible. So it is a consideration about the fact that isolated systems means that they cannot even exchange energy with the surrounding. They cannot exchange, they are just completely isolated. And there is this quantity that always grows and that can measure the irreversibility of the processes. From a statistical mechanics description, we can quantify entropy with Gibbs and Boltzmann entropies, and that somehow are a statement about the ignorance about the microscopic details of a macroscopic system. Another definition of entropy that at the first look is completely unrelated is Shannon entropy, that measures the amount of information in a transmitted message. And it is called entropy for two reasons, suggested on the suggestion of von Neumann. So the first reason is that you can see that it's almost exactly the same as Gibbs entropy. And on the other hand, no one knows what entropy really is, so in a debate you will always have the advantage. This was the tip by von Neumann. And he liked this statement so much that he decided to make an entropy himself, and he called it von Neumann entropy, which measured the distance of the system from pure state. So again, we see similarities. So information seems physical. So we seem like we're measuring these different types of information, of impurity, of ignorance, but it's not really clear why we should say that information is physical. But this is actually given by other considerations. So we said that in isolated system, the entropy should always grow, but this is not always the case. So we can imagine a thought experiment given by Maxwell, in which we have this demon, this creature that can measure the single velocities and positions of all the particles composing a gas in an isolated gas. And by this, he can separate the hot particles from the cold particles, effectively decreasing the entropy of the system without making any work. So the simple fact that he's measuring the system, that is getting information about the system, let it decrease the entropy of the system. Furthermore, we can use the same idea to produce work, so to produce an engine that is fueled somehow by the information. This is called the Szilard engine, and it was experimentally proved. And finally, we have the Landauer's principle that states that erasing one bit of information effectively dissipates heat into the environment, and this also was proved experimentally. So information is effectively a thermodynamic resource. So we can use quantum information techniques to work with quantum thermodynamics. So before talking about batteries, I need to tell you a few more concepts. So one is about timescales. Everybody knows the Heisenberg uncertainty principle. The one on the left is perfectly understood. It's about the fact that the product of the variances of non-commuting operators is lower bounded. This other one is used in many textbooks, in many articles, in more or less an heuristic way. However, the interpretation is not really clear because time is not an operator in quantum mechanics, so it cannot not commute with the energy operator. And the correct interpretation was given by Mandelstam and Tam, who stated that the dynamical time for a system to evolve between two orthogonal states is lower bounded by the inverse of the variance of the energy. And we can give a general bound for unitary evolution, so even when the states are non-orthogonal. And if we want to talk about non-unitary evolutions, we can use a more general geometric approach. I won't go into the details. However, we can describe, so we can lower bound the dynamical time to perform some quantum evolutions given the energy of the system. So this is a deep connection between the time it takes for a system to evolve and even, for example, the computational time or the complexity of performing some quantum computation. And finally, this was also as well proved experimentally even in complex dynamics. For example, non-Markovian dynamics proved that can speed up quantum processes. So finally, we need to talk about Gaussian states because the state we are going to use as a battery is a Gaussian state. So put it simply, Gaussian states are states evolving under a quadratic Hamiltonian. They can easily be described in phase space. The connection between, so we describe them with the quadratures of the fields that can be stated in terms of the annihilation and creators operators, and they satisfy the uncertainty relation. So, for example, classical example of quadratures are position and momentum. However, they can be also, for example, the real and imaginary part of the electric field. So there are many quantities, and the discrete description or the quadrature description, so in the phase space, is somewhat equivalent. This is just more practical for our purposes right now. Anyway, Gaussian states can be described by the first two moments of the quadratures, so the mean value and the covariance matrix of the system. In this work, we are not interested in the mean value. We just care about the covariance matrix. So we can fully describe the state with the covariance matrix that encodes the noise properties of the system. So it's uncertainty relations somehow. The Hamiltonian we're going to look at is the following. So it's given by the sum of two elements. One is the Hamiltonian of the harmonic oscillator, and the other one is the charging Hamiltonian. So the charging Hamiltonian is something that we will apply to the system to charge it, to give it more energy, and it depends on time, so it will otherwise we cannot change the energy, and it will be applied between times tau A and tau B, and it is a parametric oscillator Hamiltonian. It implements a squeezing. If you don't know exactly what squeezing is, it's easier to understand it in the phase space. So in the phase space is just the space of the two quadratures, and in blue you can see the vacuum state. So the vacuum state has zero mean value of the quadratures, and however it has some variance, and we normalize it to 1/2 for simplicity. And then the squeezed vacuum is defined as the state that has one of the variance of one of the quadratures strictly smaller than that of the vacuum. However, to satisfy the uncertainty principle, the other quadrature, the variance of the other quadrature, need to be anti-squeeze, so the variance will increase. Then we have the other states are in the phase space could be other Gaussian states are the coherent states, which is just the vacuum displaced with a non-null mean value, and a squeezed coherent state, which is a displaced squeezed vacuum. And you can see that the squeezing can be applied with some angle. However, in the Hamiltonian, we explicitly remove this angle because this does not influence the energy of the system. However, we will have two forms of squeezing. One is given by the charging potential, so it's a coherent form of squeezing, something that I can control perfectly. And the other form of squeezing is given by a squeezed thermal environment. So the environment in which we put the battery is something that we can engineer so that it implements a squeezing on our quantum battery. And however, this is a form of incoherent squeezing that effectively drains purity of the system. So there will be an interplay between these two forms of squeezing. And in that case, the angle in which I apply the squeezing will have a role, and I will repeat this later when this will appear. So now we can talk about quantum batteries. Batteries are systems in which we can temporarily store energy to be transferred from production to consumption centers, or even just to use them save them for later. The sizes of these batteries can range from huge vehicle traction batteries or to tiny medical device batteries. And with the boost of quantum technologies, we are reaching sizes that are submolecular for the batteries, so the quantum mechanical description is required. However, this is not the only reason why we want to take into account quantum mechanics. In fact, it was proved that quantum effects can enhance many properties, the performances of quantum batteries. In particular, it was seen that, for example, ensembles of batteries can be and can enhance the power if we are doing entangling operations. So there is some form of quantum advantage in the power of these batteries. However, these works are mostly studied in reversible unitary operations, which is theoretically okay. However, in practice, if we want to implement this, we will always have some form of noise, and it is not clear if these quantum advantages are still there. So unitary operation, this is a joke, of course, but it's kind of like that. So let's take a look at our charging scheme. So our quantum battery starts as an uncharged state. So it is the vacuum state of our harmonic oscillator that is, however, in thermal equilibrium with a thermal environment, so no squeezing, just a huge thermal state. We can parameterize it with temperature TA. However, another way to parameterize temperature is the number of excitations in the system that is connected to the temperature in this way. And why we do this is because the initial state of the covariance matrix is very simply expressed as a function of the number of excitations in the system. However, if I say temperature or number of excitations or inverse temperature, it's always the same parameter somehow. They are all connected. And so at time t equals tau a, we plug the battery to the charging potential and to the squeezed thermal state. The squeezed thermal state, is here in red, has three parameters. One is the temperature, so the number of excitation in the bath, the incoherent squeezing parameter RB, and an angle, which I apply the squeezing. So between times tau A and tau B, I perform this, I apply the charging, and the system is described by this Lyapunov equation, whose like the matrices A and D can be recovered from the Lindblad equation I showed before. Of course, I could have described the system with directly with the master equation. However, the density matrix of the system is infinite dimensional, whereas the covariance matrix has only three parameters for a single mode system, at least. And finally, at time tau B, we turn off the potential and the battery is fully charged. So let's make some energetic considerations before going into the simulations. So we said that the internal energy is the average value of the internal Hamiltonian, which is just the trace of the covariance matrix. So the energy difference will be the trace of the difference of the covariance matrices. And then we can recover the work done on the system with the formula I showed you before, and this is what we get, effectively. And finally, with the first principle, the difference between the energy difference and the work done on the system will be the heat loss to the environment. So all these quantities are important, need to be tracked and measured, but none of these represent the amount of work that the system can do, so that our battery can do once it is charged. In fact, this quantity is called the free energy and needs to take into account the second principle, so that part of the energy that we put into the system will be lost due to entropy, to the irreversible production of entropy. So entropy for a Gaussian system can be computed with this formula with its symplectic eigenvalues, which can be easily computed for a single mode through the square root of the determinant of the covariance matrix. And then the temperature is connected to the number of excitation this way. And then the free energy is a function of state, so it only depends on the initial and final state. And so in the charging phase, so in the stroke AB, I will have a negative accumulation of energy because I am putting work in the system. So the inverse of that is the work that the battery can do. And it is upper bounded by the internal energy. This is important because then we can use the ratio between these two quantities as a efficiency, and this is what we will do. So in the best case, we imagine that if no entropy is produced, in the unitary case, in fact, I will have one efficiency, so perfect efficiency. However, in all other scenarios, it will be lesser than 1. Finally, we'll take the evolution to be infinite for practicality, and also because these interactions happen very quickly. So in practice, what happens is that when you plug and then unplug the potential, the time scale is much longer than the duration of the interaction. So let's take a look at some simulations. So here we track the efficiency, defined as the ratio between free energy and internal energy. So in a first stage, we consider only one single thermal bath. The same we use for preparing the uncharged batteries is the one we use to charge the battery, and they have the same temperature. And we can see that at low temperature, which means at high purity of the initial purity of the system, we have better efficiency. So this means that quantum coherence improves the efficiency. This is somewhat unintuitive because the temperature actually, so if I increase the temperature of the bath, I actually increase the energy accumulated on the system. However, its efficiency is reduced because more entropy is produced in this sense. Now we change the temperature of the second system, we let it grow, and we use also the temperature of the second bath charge the system, and the dynamics now is more complicated. So we would expect that maybe it will be monotonic, for example. However, we see that increasing the temperature of the second system in a first stage reduces the efficiency, and then when we go really high, we actually recover the efficiency. Now we turn on the incoherent squeezing, and we see the interplay between the squeezing, which is the coherent squeezing, which is given by the parameter lambda, and the incoherent squeezing, which is given by the parameter RB. And we see the effect of the angle of the squeezing, so the difference of the angle of the two squeezing do play a role. And we find an optimal angle in this region. And however, also in this case, we would expect that squeezing that the energy always increase if I apply more squeezing, either coherent or incoherent. However, the situation is much more complex and rich, and we need to find, there is always a best region in which we have the maximum efficiency. So another quantity we studied is the power of the battery. However, the power is defined as, the average power would be defined as the free energy divided by the time, but we said that the time is infinite. So how we do that? We multiply this by the interaction time. So there is a difference between the evolution time of the system, so how much time it takes for the system to go from uncharged to charged, and the time I apply the charging potential. Okay? These two are both infinite, however, the ratio is finite. And we can compute it with the quantum speed limits this way. So if you didn't get the intuition, is that I can apply the charging potential for an infinite time, and however, the system is already very close to its final state in the first stages of this application. So I can do this, I can compute this ratio as a ratio between the distance between two states, which is the Bures distance between the two states, and somehow the average distance, which is the integral of the velocity at which the system is evolving. And so this velocity can be computed as a function of the symplectic eigenvalues. So anyway, we're taking track of the power of charging the battery. And we can see that the situation is very different than for the efficiency. So in this case, the temperature of the bath is actually a much more useful resource than the coherence of the system. So when we go to high temperature, the power of the system increases exponentially. And at the same time, when we turn on the incoherent squeezing, we can see that, again, the parameter of the angle is playing an important role. However, when we had the region in which the parameter was optimal for efficiency, this is the worst region for the power. So we have this trade-off. So we can optimize these batteries either for efficiency or for producing power. So in conclusions, we illustrated a scheme for the charging of a quantum battery with squeezing based on the dynamics of an open harmonic system that are effectively easy to produce in lab. We studied the effects of coherent and incoherent squeezing and their trade-off, and characterized the charging process by tracking efficiency and power, exploring all these parameters. And we demonstrated the key role played by quantum coherence in the charging process. Thanks for your attention.